Hello all, welcome to my course on methods of adhesion measurement theory and practice. We are at lecture 47 today. In the last lecture, we started discussing about peel test or the peel experiments, and that is what we are going to continue today. Some relevant references for the peel test can be found in this paper of Professor Kendall, and of course there are many other papers you can find later on, and some of the topics that we will cover today can also be found in this particular review article by Professor Manoj Choudhury. So, in the beginning of the last lecture, we discussed about the sandwich plate between two parallel discs, and we analyzed the pressure distribution in this elastic film, which was compressible. And after doing that, we started discussing about this peel experiment, and I discussed about the peel angle and peel this is 90 degrees say, and the rate of peeling and all that. So, I also showed you this movie. I will quickly play this movie once again, and so here in essence this adhesive which tape which is first placed on a rigid substrate and then on a flat substrate, and then is being peeled off. But when we peel, we see that the contact line has got some kind of patterns or cavitations, and as we move this region of this debonding, that propagates from the left to right. So, the tensile load that is maximum, it is very clear in this region, and then it propagates to the right. And so, let me just play it over here, and and this cavitations or this finger leg structures, they appear. There is a length scale with that. I also said that we need to measure or need to note down the rate at which this peel test is being done, because this wavelength and also let us say the peel force that are expected to dependent, or at least we are curious to know that whether they are dependent on this peeling rate. So, whenever you do this experiment, you make sure that you note down this peeling rate and do the experiment at different peeling rate in order to get an idea of how this peel force or the adhesion strength and how they are related. I will come to that in a while, are related. So, here is another video, in which case this has been done at a more magnified image, and here this is at a slower rate. The experiment has been done, and you can see here the slower rate, this cavity slits goes, but then there are this kind of finger leg structures that appear, and that goes on from the left side to the right side of this surface, and this is being done under optical microscope, and we can also see that some kind of a curved meniscus over here that also forms. So, it is interesting to note down that these fingers do not appear haphazardly, but there is a kind of length scale between them. So, we are interested in the whole thing, the whole physics of this phenomenon, how it happens, and then why this length scale that appear, and how these length scales depend upon various parameters. For example, the modulus of this particular film, the top surface, the adherents, the modulus of the adherents, and so on. So, we will come to that gradually, and not everything, but to some extent we will try to answer some of these questions. So, in a sense, the experiment is being done is something like this. So, we have this this adhesive film or this substrate on this rigid bonded to this substrate, and then let us say a load is being applied. The load is F. This W is basically the width of this adhesive tape, and then the angle of peeling is basically theta, and let us say that under this load, so basically this there is a thin layer of adhesive that remains bonded to a backing. So, there is a thin layer of adhesive glue there, right, and a thickness of this adhesive is actually H, basically that, and it is remains bonded to a backing. So, part of it is backing also, basically that I want to say, right, and the backing does not stretch and does not take up any energy, let us say, that is the basic idea. And then, but that is the basic assumption here, okay, we assume that, but that does not necessarily have to happen that way. So, now we try to apply this load, and let us say because of that this portion, okay, at a very small infinitesimal amount of, that is a delta x, that this adhesive comes out of this contact of this particular substrate. So, that has been shown over here. So, here the load is F, and now because of this delta x amount lifting that has happened. So, the question is that how much, what distance the point of application of the load that moves. So, here it so happens the delta x over here. So, the total length from here to here should be this length plus this delta x, okay. But actually the amount of distance that F has moved is not this delta x amount, because this distance over here is delta x cos theta. So, delta x cos theta, because this angle is theta here. So, this angle is also theta. So, delta x cos theta is this angle. So, the point of application of this particular load that has moved by distance delta x minus delta x cos theta. So, delta x minus delta x cos theta, it is by this distance that this particular point of load that has moved, and that is the energy associated with it. That is what we have to understand. So, the potential energy of the load that is given as F into delta x into 1 minus cos theta, then fracture energy spent for creating new surface. So, that is minus W x, and this is let us say delta x into this quantity W here, which is the width. So, this is the area, and this is the actually W, I will write represented G here, fracture energy. So, there is a difference between fracture energy G and the work of adhesion. Work of adhesion is a thermodynamic quantity, G is not. G is the actual energy that goes into the interface for separating these two adherents, and the G therefore is not only this thermodynamic work of adhesion, but also contains some other factors, other aspects it has to take care of. For example, the energy dissipation that happens or irreversibility that is there in this particular system, either in the surface or at the bulk, okay. G has to take care of both. So, therefore, G is not exactly work of adhesion. So, G becomes equal to work of adhesion when there is no dissipation, okay. It is like that. So, in any way here this fracture energy spent for creating new surface is this, and then the stress in the elastic field, so the energy that is there in this particular adhesive, that also has to be calculated. So, that is equal to, so from that we will calculate by finding out the stress in it. So, that will be equal to F, and thickness is H, and width is W. So, this is the stress in this film, and then the strain will be equal to F by H into W into E, let us say. So, E W is the width basically. So, the width, okay. So, basically H into W is the cross section of this adhesive basically, and then this is the strain. So, the energy will be equal to per unit volume. So, that is equal to half into epsilon E z z E z z into z z. So, that is equal to half, and this is F by H and W into E, and this is into F by H into W. So, yeah, it is like that, energy is like this, and it is the per unit volume. So, we have to multiply it by the volume here. So, the volume will be, so it is half here, let us say this is F square, and this is let us say H W square, and this is E here, and the volume is H W, and the amount of force, this particular force is applied, so the energy gets stored into this portion which has come out, okay, of this substrate. So, that is this quantity delta x. So, you have to multiply delta x here, right. So, therefore, this energy that is stored in this adhesive will be F square by 2 and E, and this is H into W into delta x, like this. So, this is the energy, I should say the elastic energy, okay, elastic energy, not just energy but elastic energy per unit volume. So, the total energy that we can find out ut is equal to F into delta x into 1 minus cos theta, okay, plus minus this is z here and delta x into w, and then here it is plus this is half, this is f square by 2, so E 2 is already have written. So, E h and w into delta x. So, we minimize it with respect to this quantity delta x and put it to 0, and so that will lead to f into 1 minus cos theta minus z into w plus half of this is f square by E h w, okay, will be equal to 0. So, we will get this expression, okay, this equation with respect to force that is applied. So, here remember that when we calculated this elastic energy, it is the stretching energy that I considered, okay. This is the stretching energy in the adhesive that I considered. Now, as I said that this tape is being peeled off. So, let us say it is being peeled off. So, there is a bending of this adhesive and also the backing material. So, that energy is also there, but as it progresses from, let us say from here to here. So, this bending energy that remains same. So, as it goes from here to here progresses, this bending energy does not change. So, that remains constant. So, therefore, I did not write it, but it is actually should be there in this total expression of the total energy. Bending energy should also be there, but this is constant because as we make progress from one point to another, this bending, this particular profile we assume that does not change, that continues to remain same. So, therefore, this remains same. So, therefore, we have finally this particular equation. So, yeah, so we have this equation over here, and we can, so this is a quadratic as you can see with respect to f by w. So, basically we can write here f by w whole square, let us say whole square, and then we can write here plus 2 f by w again w, yeah, f by w into 1 minus cos theta into this is I have multiplied by 2 and EH 2 EH. So, I have multiplied by 2 EH all the terms, okay, and divided by W here and minus G into 2 EH, okay, this is equal to 0. So, I have actually rewritten this equation to get it in terms of F by W over here. So, that is what I would like to do now. I would like to find out what will be F by W. So, that will be equal to minus of 2 and this is 1 minus cos theta into E into H and plus minus this should be B square minus 4 AC. So, it is a usual thing. So, it is, let us say it is B square is 4 here, 1 minus cos theta whole square E by E into H B square minus 4 into this is G into 2 E into H by 2 here. So, it is like that. So, B square, this should be plus here, B square minus 4 AC. So, minus minus plus here should be plus like that. Now, what should be the sign over here? Now, F has to be positive, and taking that consideration we should have only the positive sign over here, and so therefore, I should have here minus divided by 2, it is 1 minus cos theta into E into H, and let us say it is plus here, okay, divided by 2. So, it is 4, and so here it is, let us say 1 minus cos theta whole square and E H whole square plus, now divided by 4 here. So, it is 2 E H into G. So, what I can further do is I can take this power portion common. So, E cos theta into E into H plus, let us say 1 minus cos theta into E into H, and let us say that I will take it as 1 plus, let us say 2 E H into G by this is E into H into 1 minus cos theta into square root half. So, of course, this E H and E H this goes. So, I can do this. This is basically the solution of this particular equation for this F by W here. Yeah. So, this is what I have it. Now I have 1 minus cos theta whole square. So, I have to write a whole square, should not miss it, cos theta whole square here, right. So, and oh sorry about that, this is EH whole square here. So, this EH when it goes, so it will be EH remains. So, EH into 1 minus cos theta whole square, that remains over here. So, that is what I have here. So, now what we can think is something like this, that this elastic modulus of this backing layer, okay, that is actually quite strong, and so therefore, that does not contribute much to the deformation or the energy. So, therefore, we can also think that this F by W, let us say, into E into H, okay, that term is much small with respect to 1. Also we can say that this term G over EH into 1 minus cos theta whole square, that also smaller than 1, something like this. So, basically in essence what we are trying to say is that the energy that is spent by peeling, applying the peeling load, that basically goes into this fracture energy part, okay, in separating this adhesive from the substrate. The energy that is taken by this adhesive and its backing, which is represented by this particular term, that is actually small, basically this part, that is actually small. So, it is on that premise that we can write this quantity as we can write this quantity, we can something like this. This is, let us say, F by W is equal to minus, this is EH into 1 minus cos theta plus, this is EH into 1 minus cos theta plus EH into 1 minus cos theta, EH into 1 minus cos theta into 1 and minus, this is half, and this is, let us say, G 2G, right, into EH by 1 minus cos theta square. So, this is 2G, this is EH into 1 minus cos, sorry about that, 1 minus cos theta square, like this. So, therefore, let me take the whole thing as, so this is, let me take it like this. So, EH into 1 minus cos theta. So, this is that simplification that I did. So, square root term I wrote it over basically an series expansion, and then I leave out the higher order terms. So, I take only this particular term. So, basically that is what has been done here, plus this is EH into 1 minus cos theta, and then here it is minus, this is 1 plus, yeah. So, here it is minus, so it is should be minus, then 1, then plus actually. So, it is plus here, damn it. So, here, yeah, plus, so here it is, here this is this term we will actually simplify it. So, basically let me simplify it as, oh, this is plus here. So, I should have plus here, plus here. So, this is plus plus half, and the 2 gets cancelled, and so therefore, I have G by 1 minus cos theta, like this. So, this term and this term gets cancelled. So, in essence what I have is F by W is equal to G over 1 minus cos theta, and this gives the G expression of G in terms of this peeling load. So, F by W into 1 minus cos theta. So, this is a very simple expression that we get for estimating the fracture energy from the peel force. So, the peel force is F, and per unit width, that is F by W, and then you multiply it by the cos theta, theta is the peel angle. So, what it means is that if theta is cos theta is 0, that means theta is pi by 2. So, for theta will equal to pi by 2, okay, 90 degree peeling, okay, you will have G is equal to simply as F by W, very simple, okay, expression. That is why this peel test is very popular, okay, because you can directly get an expression of the fracture energy. So, fracture energy is the one for all practical purposes, that is what matters, right. And so, therefore, it is very easy. Now, if theta is equal to pi by pi, let us say theta is equal to pi, then it will be cos theta is minus 1. So, minus 1 plus 1. So, it will be 2 into F by W. So, we can do the experiment that way also. So, in essence what I mean to say is that this G, okay, that depends upon this angle theta, the estimation of g, the value of g depends upon that cos theta. So therefore, whenever we do this experiment, okay, we have to find out this, take care of this particular term, this peel angle, okay, that needs to be measured and that needs to be noted. Now let us say that let us say that theta goes to 0. So it is a 0 degree 0 angle peeling. So if theta is equal to 0 here, then this term will be equal to 1. So 1 minus 1, 0 here. So what we will have is f by w is equal to square root of 2e into h into g. So like that, right, because here this theta goes to 0. So it means that, now what does it signify? Now this signifies that there is a substrate and then there is an adhesive tape here. Let us say adhesive tape is something like this, bonded to this substrate and by this glue over here, and then you are peeling it. So in a sense this is defines the shear joint, right, shear joint or shear separation, basically shear joint, right, and this idea can be further extended. So here it is like this. So this is basically a shear joint. So thin layer of adhesive is there, thin layer of glue, and then these two surfaces are being bonded and they are being sheared off. So the fracture energy should go something like this, the peel force or the shear force should go something like this. Now one may also have this double lap shear joint, it is called. So that was a single lap shear joint, this is a double lap shear joint, and since there are two layer of adhesive there, so therefore this quantity f by w will be equal to 4 eh into g, that is the failure load for this double lap shear joint, right. One can also extend these ideas for the delamination problems. So for example, there are one material, one particular layer, okay, which is bonded to another layer, but they are dissimilar in the sense that here the modulus is E1, here the modulus is E2, and here it is H1 and here it is H2. And delamination of paints and delamination of thin sheets, these are common phenomena and that we see all the time, and you see in most cases these are two dissimilar materials and there is a dissimilarity that happens at this interface, okay, across this interface, and because of that there is a failure that happens. And what is the kind of peel force that is required for failure to happen is given by this particular kind of formula, where G is the adhesion or the fracture strength of this interface, and H1 and H2 are their thicknesses correspondingly. And one can actually derive this expression, which is basically an extension of this particular relation that we have just gotten over here. So these ideas can be further extended and one can get the peel force for this kind of situation, basically delamination. So there are lots of problems on lots of papers, interesting papers on delamination. If you are interested, you can read, but this is the basic idea that I have just shown you from Kendall's paper. Now there is a problem, let us look at this problem. So this is a typical peel test that has been done. Let us say there are like two different adhesives. So each of having width of 1 centimeter are peeled at an angle 60 degree, okay, of an substrate at different peeling rates. So these are the different peeling rates, and when you peel it you have to measure this load, and that the load cell gives, let us say, the load in grams of weight. Following peel force data are obtained at different peeling rate for the respective tapes, tape 1 and tape 2, which are presented in table 1 and table 2. Obtain how the adhesion energy depends upon the rate of peeling of these tapes, and comment also on their nature of adhesion to the substrate. So that is the question. So here what we will first do, we will like to plot this V, that is the plot this, let us say the weight peel force, okay, as a function of V, and peel force is M. So so M is in gram, so it is in gram, let us say. So first take it to again 10 to the power minus 3, multiply it, make it kg, and then multiply it further by this acceleration due to gravity. So let us say I take it as 10 only, so 10 Newton per meter square. So this becomes is equal to Newton. So let us say this much amount of Newton force. So this is the way I obtain the peel force that has been applied and then we know that G is equal to F by W. So, I have to multiply it m divided by centimeter, right. So, we have to do it that. So, divided by centimeter 1 centimeter. So, it is 10 to the power minus 2 meter, 10 to the power minus 2 meter, right. So, like that. So, you multiply. So, 10 to the power minus 2 to the minus 1. So, it is actually m only, good. So, m Newton per meter, and then G will be equal to F by W into cos theta, whatever to 1 minus cos theta. So, 1 minus cos 60 degree is equal to half, and that is into here it is m, this is Newton per meter square now. Now, Newton per meter, m into Newton per meter. So, this is Newton per meter means Newton meter per meter square, joule per meter square, that is the way it is. So, cos 60 is half, remember that cos 60 is half. So, here what we have is m by 2 into Newton meter per meter square, that is all I have. So, this is what I have to do over here, and we have to do this calculation. So, here first let us see, we have plotted this m as a function of v, and what we see is that for table 1 data, okay, there is a variation, significant variation of m with respect to this peeling rate. On the other hand, for the table 2, there is little variation initially, after that more or less it remains constant, variation is actually too low. So, the way that we just described, we actually calculate what will be this Newton meter per meter square, joule per meter square, and we did all that. And so, here, yeah, so I have already done all this, and then finally we have these values, and then we plot it. So, the plot also G also will be expected to look something like this, and then we plot it for this case it is like this. So, now we want to know that how this G goes as V. So, what you do is that you write ln of G, okay, as a function of ln of V, okay, ln of V. So, let us say that G goes as V to the power n. So, therefore, ln of G will be equal to n into ln of V, like this. So, you plot ln of G and ln of V with the slope n. So, that is all we have done here, and we can see that when you plot this ln of G as ln of V, we get a straight line. The data falls on a more or less in a straight line, and so that the slope here is 0.5, and for this data, for this table 2 or the tape 2, this slope comes out to be 0.1. So, what it means is that this for tape 1, okay, this is a rate dependent fracture that happens, rate dependent fracture. So, okay, on the other hand, G where V to the power V is to the power 1 by 10. So, here also rate dependency is much low, okay. So, almost like rate dependent, okay, that is what we can say, rate independent, almost rate independent fracture. Not only that, we can also say that for this kinds of rate dependent fracture, this is a kind of viscoelastic dissipation or the surface rate dependent dissipation that happens. So, there is a dissipation that is present for this step 1 case, but that dissipation is not there, okay, or even if that is very low, okay, in this particular case. So, very low dissipation or irreversibility in the film, in the material dissipation. So, what it also means that the kind of G value that we get here. So, for example, okay, we can find out an average of, let us say, okay, whatever is the average, that is the kind of G can be equated to work of adhesion, but that is very close to the thermodynamic work of adhesion, because that irreversibility has not led to any amplification over here. So, that is all. These are the various things that we can say. Now, why this happens can be because of various reasons. One is that the adhesive itself may be elastic, not viscoelastic, and other things can be that there is the surface at which this is attached, the surface it is non-dissipative interface, in the sense that there is rate dependency is very low. So, normally if at the interface, if the substrate has got Van der Waals type of interaction, okay, so this is the adherent substrate, So, if the substrate has got Van der Waals type of interaction, okay, then there is very low possibility of rate dependence. On the other hand, if there are hydrogen bonding and other functionalities, then this rate dependent might increase, okay. So, these are the various things we can say about these results over here that we presented here. So, that is all for today. In the next lecture, I will like to present some real results from experiments, okay, about this contact line deformations, like contact line, the way that contact line becomes wavy and undulatory. So, we will see some results from that, and then I will like to talk, go into this bending aspect, okay, of this film, okay, the bending, that when you do the peel experiment, we also bend at the contact line. So, this adhesive and with the backing. So, we will look into that aspect in the next lecture. Thank you for today.